Hello, everyone, and welcome to the Daily Space for today is May 14th. Now, you can see this cool window up above me. This is NASA TV, which is about to bring us live coverage about a new discovery with Europa. So I'm going to click over so you can hear.
Europa, we were led to the conclusion that there must be an ocean just beneath the icy surface of the moon. But there were some strange signatures in the magnetic field that we had never really been able to account for.
Images of Europa from the Hubble Space Telescope have hinted at gases that might have come from plumes erupting at Europa.
The Hubble images had given an estimate of the height and width, and I knew how fast Galileo was moving relative to Europa.
There are better tools now, better computational techniques, better computing, that we can go back and look at that old data set anew.
So my colleague Shinja Jia set up a calculation to see what would happen in the environment of Europa if there were such a plume. And when he ran this simulation, it agreed just beautifully with the data that we had collected.
Reanalysis of the Galileo magnetometer data suggests that the Galileo spacecraft, on its closest flyby of Europa, flew through a plume. The Europa Clipper mission is going to explore Europa to investigate its habitability. If we find active plumes, then we can sail on through them and sniff and taste that stuff that's in the plume. We can analyze the particles and the gases to get at the detailed composition of Europa's interior.
And here we go.
Good afternoon. I'm Lori Glaze, the acting director of the Planetary Science Division at NASA. And I'm really excited to be here today talking with planetary scientists about this recent result confirming plumes on Europa. I'm joined today by my co-pilot, Joanna Wendell. Joanna is a communications specialist here at NASA. And to my left is Dr. Elizabeth Turtle from the Johns Hopkins Applied Physics Lab. Zibby is interested in the moons of the planets in the outer part of our solar system. To Zibby's left, we don't have her yet, but we have Dr. Shinja Jia, who led the research that we just saw about in that video. And Shinja is from the University of Michigan, and he's interested in magnetic and plasma environments on the planets and their moons.
So these
and
are
I'm hoping
young
we'll also be
researchers,
joined
which is part
by
of why
Dr.
they're
Margaret Kivelson
using
from the
archive
University
data.
of California, Los Angeles, and she was a scientist on the Galileo mission. And she led the magnetometer investigation that discovered the ocean on Europa. So with that, I think I'd like to toss it over to Joanna, and would you like to kick off this discussion?
Yes, I would. This is a super exciting new line of evidence for Europa plumes, which is awesome. But I think before we really get into the nitty-gritty of these findings, we should really back up a little bit
computer.
and
it shows which world
figure
she
out
works with.
what is Europa and where is it?
Europa is one of the large moons of Jupiter, the planet Jupiter. It's somewhat smaller than our moon, and out at Jupiter's distance from the sun, Europa's surface is covered in ice, in water ice.
Yeah.
But beneath that water ice layer, there's evidence that there's a liquid water ocean.
Wow.
Which is really exciting.
That is so exciting. And it's so far away from the sun. So we know it's covered in ice, but how does an ocean survive out there? A liquid ocean survive way out there?
Well, there's an interaction between the different moons of Jupiter.
Yeah.
Io, which is the closest moon to Jupiter.
So what they're
Europa,
talking about here
and then
is
Ganymede.
how Europa is getting
they're in what's called a
tidally
resonance,
heated.
Yeah.
which means kind of like when you're pushing someone on a swing.
Yeah.
Every time they come back, you give them a little more
Yeah.
push, and the moons do the same
Cool.
thing to each other. in their orbits, and that actually generates a lot of energy.
Wow.
So Io has silicate volcanoes, just like Kilauea that's erupting right now.
Yeah.
Right.
And as you move further out, the moons get progressively colder.
Okay.
So Europa still has an icy surface, but a liquid water ocean underneath. A fairly thin ice shell, and
So
as you
feel
get out to
free to
Ganymede,
ask
there's
questions.
a thicker ice
Yes,
shell.
plumes
but
as in
also
geysers.
with,
These are
a liquid
ice
water
geysers.
Ocean
But the
in
heat
interior.
keeps the water liquid beneath the icy
Exactly.
crust.
Yes.
Wow.
Yeah.
Yeah.
So then what is a plume?
So one of the questions that we've had about Europa with this fairly shallow ocean is whether or not there's current activity at the surface. And one way that kind of activity can manifest itself is
there's
by what
current
we
activity,
call cryovolcanism,
that means we can
which is
sample
cold
the
volcanism.
water
Whoa.
without having to
And we
dig a
see
hole.
that at Saturn's moon, Enceladus,
Okay.
where there are large plumes of liquid water and ice particles that are jetting out of the south pole of Enceladus. But it's been a long-standing question as to whether we have that kind of activity at Europa as well.
Yeah. Oh my God. I mean, that's so. Like, how do you even go about trying to find plumes? I mean, what are the different techniques we've used to even find these things? And either of you can.
I don't know, maybe you should
Volcanoes are
talk a little
truly
bit about
in fashion.
Yeah, I mean, of course, from telescopes,
These are just
you
ice
could observe
instead.
existence of potential plumes. So that was actually being done back a few years ago when Hubble first sent back images in 2012, and the scientists have found, hints that those images might contain signatures of potential plumes at Europa. A couple of years later, they obtained further images and actually saw plumes occurring potentially at other locations from the first detection. So telescopic observation certainly is a very useful, valuable tool to search for plumes.
I just wanted to interrupt for a second. When you say that Hubble sent back images, I mean, are we talking about point and shoot image, and we see the vapor, sort of cloudy? I mean, when you say image, what are we actually seeing with our eyes in this image?
Yeah, so there are two kinds of, I think, techniques are being used so far from Hubble. The first set of images taken by Hubble, we're looking at the emissions of molecules being struck by electrons that would generate emissions, and those emissions at a specific wavelength will be captured by Hubble. And the follow-up...
We'll be talking about that helicopter later.
Similar process?
Yeah, similar process. And the follow-up observation from Hubble, I believe, was looking at actual absorption of atmosphere water molecules of the lights. So the two different kinds of techniques are so far being used to look for plumes.
Okay. Cool. So but how did we discover them this time? So this was what I understand is that we knew that there were plumes, or we believed there were plumes from the Hubble observations. But you and your team went back and looked at the older data from the prior mission, from Galileo. Can you tell us a little bit about the Galileo mission, or maybe Margaret can tell us a little bit about the Galileo mission and the instrument that she led there?
Yeah, let's get Margaret.
Can we get Margaret
Hello?
On here.
Hi. Can you tell us a little bit about the Galileo mission and the magnetometer instrument and investigation?
I love to talk about the Galileo mission and the magnetometer instrument. So the Galileo mission reached Jupiter in 1995 and was there for 8 years in orbit for spacecraft in orbit around Jupiter. And one of the key parts of the mission was to make close flybys of the 4 large moons of Jupiter.
So this is a woman who
there
was
were 11 flybys
a researcher on a
of
mission
Europa,
that
and
ended
in a
in
flyby,
2003.
The time close to the moon is of particular interest because that changes the way in which the charged particle gases in the vicinity of the moon move. It slows them down, it diverts the flows, and changes the magnetic field. And so for each pass, we looked at changes in the magnetic field that were associated with approaching the moon. And on one particular pass by Europa, the spacecraft came very, very close to the surface, as I remember, less than 150 kilometers above the surface. And it was on that
I think the smaller
path that
tables
we
are just the
saw
tables they needed
signatures
because
that
they
we
had
never
too many
really
people.
understood. So I don't know if you want me to go on at this point. Or,
Well,
That was great.
Happy
my
scientist
helpful,
is
thank you.
happy.
yeah, so my question then would be, what inspired you to go back into this, 20-year-old data, right? You know, there was this signature that maybe you never understood, but what was the thing that made you go, oh, maybe we should check that out again? And, either Shinja or Margaret can address.
The plumes that we're talking about,
well, you can start.
they
Shinja.
can't quite
Okay.
say definitively.
And I think really we're largely
that this
inspired
is
by those Hubble
water.
detections
What they
published
can
back a few
say
years ago.
is
As I
there
remember,
are
almost
geysers
exactly a
that
year
are
ago,
spewing material
we
from
had a
beneath the
Europa
surface,
Clipper
whatever that
Project Science Group
liquid
meeting
might
in
be,
Columbia, Maryland.
out
The fifth meeting
above
we
the
had.
surface of
So
the
all the team
ice where it
scientists
can
were
be
gathering
sampled.
together and talking about science related to Europa. And one of our colleagues, Melissa McGrath, so she was showing a summary of all the available Hubble images we had so far of Europa potential plume detection. And the latest paper was just published about a month before this meeting. So she was talking about, the locations of potential plumes in those images. And that is the moment that really, I think, led us to realize that we had to go back to look at Galileo data, because one of the flybys, as Margaret just mentioned, had a closest approach altitude that's just a couple hundred kilometers above the surface in a region.
This is important because
plume detection by Hubble.
we'd seen the plumes in Hubble data, but it hadn't been realized before the Galileo mission ended. So they're going back to see, did Galileo detect things that we didn't know were there? And the answer was yes. Yes, Galileo did that.
Flying over Old Faithful Geyser in Yellowstone. I mean, what do we think is going on there?
Well, it would be very tenuous. You'd be able to sense it. Clearly, Galileo sensed it,
Yeah.
but Galileo didn't see it.
Okay.
So optically, it's not necessarily very optically thick.
Okay.
Is how we'd refer to it. There are not a lot of particles, which is good, since
hard to-
Galileo
Yeah,
flew
it didn't
through
get
it.
shot, out of orbit.
But we do have some example from the Cassini spacecraft that did observations of Enceladus and its plume. And in terms of the imaging observations, if you look at the plume, if you look at Enceladus and hopefully Europa,
Yep.
when the sun is on the other side, so you're kind of looking through the plume
Yeah.
of the sun,
Yeah.
the scattering
Yeah,
by particles in the plume makes
Okay.
make them stand out very well. And we
Okay.
have beautiful observations of the plumes of Enceladus, and
Yeah.
that's something that we hope to do in the future
Yeah.
with Europa as well.
And
So cool.
slightly silly question, could it have seen a rainbow? Like in the mist, like is there like
that's
enough
a silly
mist here
question.
that maybe they could any kind of plume fly could see a rainbow?
No.
I've always wondered that.
I don't know that there's enough signal at the different wavelengths
wavelengths.
to be able
Okay.
to
Right.
pull that out, but
Get
we
it,
will.
yeah.
With Europa Clipper, look at
you
plumes
go.
with a variety of wavelengths. So
Awesome.
stay
Perfect.
tuned.
Maybe our first interplanetary rainbow
Yeah.
coming up.
And
It
presumably you'll do the
doesn't
same
work
sort of
like
experiment
that,
where you can put the
but
sun behind
okay.
the plume and see it, and perhaps see if it's possible to optically see it.
So
Exactly.
Astro,
Exactly. That's one of the things that we've
okay.
worked
they
into
weren't
the
looking
plans
at the
with
plume
both
at
the
the time of
cameras
the
on Europa
spectrograph.
Clipper and the ultraviolet spectrograph, which will be much more sensitive. But there are a number of other ways that we can look for current or recent activity. In terms of, you can look directly for it. You can also look for thermal signatures or
what does that mean?
particulates. So you can look to see if there's heat
Okay.
coming from the surface. And
Yeah.
in fact, there is some evidence that there may be heat near the same region that the plume was seen, correct?
The data that she's talking about comes from the Hubble Space Telescope.
Falls within the general region that we call thermal anomaly that has been observed back again in the Galileo era, published by scientists in the 1990s. And so it appears to be that general region seems to have elevated temperature compared to the surroundings.
Okay.
And why is that interesting? If there's a region of heat, we're talking, of course, about ice, so it's not hot, but hotter.
But it's hot for
It's
ice.
hot for
yes.
ice.
Yeah.
So
Yes.
what is the significance of that thermal anomaly? So this region of elevated temperatures.
So that would tell us that it would give us information about how much activity there is, how much heating is going into Europa, how it's being focused. It also helps us understand the nature of the ice shell itself.
Okay.
And one of the things we're particularly interested in is exchange processes where we may get material like a plume, where material is coming from the ocean through the ice shell to the out above Europa.
Another cool point that she's not hitting on is the warmer ice actually has been shown here on Earth to allow complex carbon molecules to form.
Looks like we have a question from the media here, a question from Will Dunham from Thomson Reuters. And the question is, to what degree do these findings suggest that Europa possesses the conditions to harbor microbial or other life forms? And do these findings change your views about Europa as a leading candidate for hosting life?
This is the question that will decide all the headlines.
Well, we know that Europa has a lot of the ingredients necessary for life. Certainly for life as we know it. There's liquid water, there's energy, there's some amount of carbon material. But the habitability of Europa is one of the big questions that we want to understand. And one of the really exciting things about detection of a plume is that means there may be ways that the material from the ocean, which is likely the most habitable part of Europa because it's warmer and it's protected from the radiation environment by the ice shell. So there may be ways for material from that ocean to come out above the ice shell, and that means we'd be able to sample it. So that's one of the reasons this is so exciting.
Just to sort of back up about the Galileo data, was Galileo able to tell what was in the plume?
So Galileo mission ended in 2003. This means that we're actually looking at 1980s technology.
Wave data.
Okay.
They do not directly tell us the makeup of the plume, the composition of the plume.
Okay.
What we inferred was, it's likely, highly likely, given the composition of the near surface material on Europa, and we think it's, if it's a plume, it's largely composed of potentially of water.
Okay, great.
Cool. I think we have another question.
All right.
Another question from the media, from Chris Gebhardt at nasaspaceflight.com. And the question is, what kind of impact do you anticipate this having on the upcoming Europa Clipper mission, and will any instruments or mission aspects be tweaked? And I think this is kind of a general question for all of us. I know Zibby's very heavily involved in the Europa Clipper. She's actually leading the cameras on that mission. So I'm sure she has thoughts, but I'm kind of opening it up. I'd like to know if other people think that this could have an impact.
I don't think it will tweak the instruments at this point. The instruments were specifically selected to be able to search for and study exactly this kind of activity. So we have the right instruments already on board. Whether or not the trajectory can be tweaked so that the spacecraft flies closer to this area. We were obviously limited by the laws of physics, so can't get to every part of the surface close up. But that's an area that would be able to be tweaked.
So
as
will
well
the
as
orbits be able to get deep enough to get down and fly through the plumes again?
So the closest approach altitudes for Europa Clipper get down to 25 kilometers.
Wow.
So they're very close. Now, whether that 25 kilometers can be done.
Oh my God, that's like.
That's an altitude we get to regularly with other worlds, so not that big a concern.
Is limited again by the trajectory of the spacecraft. So I don't know if you've looked at how close Clipper gets to that area.
I think in general, as far as I know, as its current plan is, Clipper, as you just said, ZB, will conduct more than 40 flybys, close flybys of Europa, and over 40 of them will have flyby altitudes at close approach less than 400 kilometers high. And that certainly itself is good news because the plume we identified in this study, we saw the strong signal between the altitudinal range of 200 to 400 kilometers. So the closer you get to the surface, probably the chance you're seeing signatures of plume will be higher. So I think in that respect, Clipper certainly is in a very good position. And so I think maybe the project, we have to look more carefully at, which region is being covered by all these very low altitude flybys.
Right.
Okay.
Interesting.
So it's less about the instruments changing and more about maybe where we send them or,
Right, and the observational
Right, and
strategy,
the
right? This
observation.
gives us
At this point, they've already funded all of the instruments for Europa Clipper, and there simply isn't the capacity to change any of that. What you can change on the fly, even after launch, is software and orbital planning.
The ability to fly through the plumes and identify that the plumes are there. But what types of measurements are we making other than just looking at them? But are we taking chemical measurements and trying to understand what type of chemistry is going on in those plumes? And do we have the ability to say, yes, there is microbial life, or yes, there's a potential for microbial life? So that's a question.
If only.
We do have instrumentation to be able to detect particles, to be able to make chemical measurements. There's a mass spectrometer that would be able to tell what the chemical components of the plume or the atmosphere of Europa. Europa has a very tenuous atmosphere, but nonetheless there's material there, and so we'd be able to look at that.
Right.
Put another way, if there's microbes, our detector will take them apart and measure the individual atoms that compose the microbes. But you don't get to see the microbes.
To being able to detect.
I know, it's a big jump.
Yes.
That's a really, and I think it's important for us to all really understand just how
Yes.
hard that is to do,
Yeah.
to actually say we've detected something
Right.
that's alive.
Yeah.
That's a really big jump.
Yeah,
Right, so we have to take the steps in order to get there, right?
Yeah.
Right.
To get
Yeah.
all
Yeah.
the way to that.
unless, we put a GoPro on it and see the flying space lizards. I don't know. If only.
If only. So we have another question here. This is from Twitter user Manish. He asks, why is Europa considered by many to be the most likely place in the solar system to find life?
Great
So
question.
it's a good question. It is certainly one of the, a high probability location in the solar system. It's certainly not the only location that we've
Right.
identified in the solar
Right.
system that could potentially
Right.
be a place where life is harbored. So just some thoughts there.
Well, we know there's liquid water, and that's, of course, for life as we know it, required.
Right.
And so that's one of the reasons. And at Europa, the liquid water is fairly close to the surface.
Right.
But as you say, there are a number of places in the outer solar system.
There's research that is showing that there may be waters close to a few kilometers below the surface in a few places on Europa, while most of the time it's much deeper down. So there's hot plumes that are heating the surface in different places, making it thinner.
Of Saturn.
Right.
So they're a little bit further out.
Yep.
But, do you think we're more likely to find life on Europa than at Enceladus or Titan, or is it fairly even, or is it just more challenging in some of the other environments?
It's hard to say. I mean, that's one of the reasons that habitability is such a key thing to study, because we really right now have only the one data point.
Right.
And so what we want to do is gather more data points, and we have different environments at these places. Titan, for example, has a very rich carbon chemistry, and so it's kind of a carbon world as well as an ocean world, and so that's a different dimension in terms of the question.
The important thing about Titan is methane can exist as a liquid, a solid, and a gas, which allows it to act as water does on Earth.
As on Enceladus. So we were talking about, we know there's plumes on Enceladus. We now have plumes on Europa that are confirmed. So is it the same physical process that's causing these plumes?
And maybe we can start by talking about what are those processes.
Right.
What do we think is causing the plumes, and is that maybe also happening on Europa?
Right.
Okay.
So, Shinjo,
Yeah, I think there
what do you
have
think?
been suggestions, theories, models being put out, trying to understand, for example, in Enceladus, why plumes exist, at the Enceladus, there were the suggestion has been, this tidal flexing.
Right. Right.
When you have a ice cover floating above a liquid layer, and as the moon is orbiting around its parent planet, I mean, Enceladus is Saturn, and the Europa, we're talking about Jupiter. So it changes its distance relative to the parent planet. So this flexing is changing as well. So depending on the orbital phase, how close and how far the moon is away from the planet, you might see at some locations it's squeezing, trying to squeeze the moon and making this material coming out into space. And that has been, I think, fairly well established at the Enceladus when Cassini sent back a lot of data that allow scientists to see this correlation, the orbital phase.
At different places in the
I love the idea that you squeeze Europa and liquid comes out.
That's the thing we still don't quite understand, I think, at the Europa, because of very sparse, very few data points we have so far.
Yeah. And when you say this, the flexing sort of squeezes the material out, do you mean like squeezing a toothpaste tube and the toothpaste comes out? It's kind of squeezing the,
I think it's more a case that when there's extension in that region, when the crust is stretched, it allows material to escape. And then when there's compression, when it's being pushed together, there's less material that escapes.
Yeah. Gotcha.
Right. We've got another great question here. We've got lots of good questions. Question from the media, Jesse Shanahan from Forbes Science. What is causing the unusual heating in this specific region? So this is another great question for Shinja.
Yeah.
See that it's warmer there, but what do we think is happening?
Yeah.
I think the exact origin of my understanding of reading, the literature has been the exact origin of why this particular region seems to be warmer than other places is not really very well understood. There are, I think, different models, theories being put out trying to explain this thermal anomaly. Could be internal, but also could be tied to the surface material. The thermal properties are different due to other processes. So I don't think we really know exact origin of the anomaly at this particular region.
Or how long-lived it is.
Yeah, how long it lived, yes.
Exactly.
That's a good point.
One interesting thing about Europa is its surface rotates at a different rate than its innards.
A bit of a, not geologic timescales, but a few decades worth to compare and look for changes, and so that's going to be very interesting as well.
Absolutely, yes.
Yeah. We've got another great question here. Facebook user Sarah asks, to clarify, are these pop-up storms? So looking at the radar now won't be helpful in determining timing of the storms.
They aren't so much storms. They're geysers like we have at Yellowstone. These are hot water geysers.
This isn't like a weather phenomenon happening. We aren't getting thunderstorms or anything like we said earlier.
No.
Europa has a very tenuous atmosphere, so what's actually happening is these, I know some people say geyser-like sort of eruptions of water are coming out of the actual surface of Europa.
Right.
And so, can we use data to look at the timing of the eruption?
Right. Now, and we can do models, for example, to look at how long it would take to heat up that much of the crust, the area that we see. If it's something that's penetrating the entire crust, which at Europa is 25 plus or minus something kilometers
meaning
thick,
coming from
if
directly.
A lot of this modeling work was done by Brittany Schmidt, who's currently at Georgia Tech and is our lead scientist for Vesta Mappers here at CosmoQuest.
It takes a long time to break through the crust.
So if it's not coming from the ocean, what is the alternative? Where else could it be coming from?
Yes, that's a good question. There could be diapirs or areas in the crust where warm water has risen up in the crust and is closer to the surface. And there are some areas, we call it chaos terrain, that are just they're just spectacular on,
cool
on
name.
Europa. And if you look at them, you can see they're plates of Europa, the shell, and you can see how they've moved around on top of this region. And so that suggests that there has been mobile material, possibly liquid water at depth, that they've been able to move around on, like icebergs, in the sea here on Earth.
So before we go to the next question, if I could, so I think one of the things
The graphic they just showed showed inclusions into the ice shell where hot water had carved out places to create subsurface lakes between the bottom of the ice and the surface of the moon.
An analogy you could use for, where magma is on Earth, is it like a hot spot versus, a magma chamber under a volcano? I mean, I don't know. This might not be the right crowd to ask.
So one of the
but is that I'm trying to imagine?
Right.
Yeah.
One of the complications is that we don't know what's under the ocean.
Okay.
Right? And we don't know if the interior of Europa, for example, looks like Io, which has large silicate volcanoes.
Right.
And so if there is volcanism under the ocean, the same way we have sub-ocean volcanism on Earth, then that could be one of the reasons that you get regions of heating.
Okay. Yeah.
The sub-ocean vents, volcanoes that we have in the Atlantic are sources of a massive biodiversity, and it's hoped that similar biodiversity could exist around volcanoes sub-ocean on Europa.
How many plumes, and are you able to characterize them in that way?
Yes, that's something definitely we had spent some time looking at in doing this study. So when we first saw the data, the magnetic field data and plasma wave measurements, and we, spotted out this 3-minute long signal that seems to be very unusual compared to all the other flyby data we have looked at near Europa. And again, based on the knowledge we learned from studying Enceladus, we know, when you have a plume in outer space, they're able to influence the magnetic field. They're able to influence the plasma environment. So that's kind of the information, the background knowledge we already had from studying Enceladus, and that guided us through our analysis. But to really make sense of the data, to really interpret the data, we had to go for numerical modeling. And it's exactly during the numerical modeling we had to test different plume models in terms of location, in terms of its size, in terms of its density, column.
So essentially, they're trying to figure out what conditions does the ocean need to have to reproduce what we see with the thermal images and the direct images of water going into space. He's using all the fancy science words that mean, how do we make the planet that we have, the world that we have in our software, match the world that we see with all of these different orbiting missions?
To the observations for the magnetic signal and plasma wave emissions.
Very cool.
So Galileo spent 3 minutes within the plume, or is it 3 minutes of data and the amount of time it spent within the plume is narrower than that?
The magnetic signal definitely shows a bend or a twist of the magnetic field about 3 minutes long.
Okay.
And so not only the magnetic field strength changes abruptly, it goes up and drops very quickly within that 3 minutes, but also its direction, because the magnetometer is able to tell us the direction of the magnetic field. And it also showed the very strength, the bending, the bend of the field lines.
Interesting.
And that's one of the things.
So what he's saying, put in better language, or at least less complex language, with Galileo, when they flew very close to the surface, they were able to detect changes in the magnetic field measurements they were making that was indicative of the spacecraft passing through an area where a geyser was active. And this detection was made for 3 minutes. So by seeing a change in the magnetic field for 3 minutes, we assume that the plume went for 3 minutes.
That's
right, which means that it could be even broader, closer to the surface.
Yes, potentially, yes.
We have another question from the media here, and this is kind of following on to a question we were talking about a little bit earlier. The question...
I'm amused to note that all questions from the media are just questions, and all questions from the public are very good questions, or excellent questions. These adjectives are amusing.
Compared to the ones on Cassini. So we've already talked a little bit about the ability to detect biomarkers, but it's a good question about how the instruments are similar or different from what flew on Cassini, because Cassini did fly through the plumes on Enceladus and made some observations there as well. So it'd be interesting. Can we
Like Cassini, Europa Clipper has a suite of instruments that are designed to work together to understand, in this case, Europa as a system. And some of those instruments are remote sensing instruments like cameras, spectrometers that measure things from afar. And then others are instruments that measure things in situ or in place, right in the environment of the spacecraft, like a magnetometer or the plasma instrument or the mass spectrometer, for example. One of the big differences is that Clipper has a sounding radar. So that allows us to get information about the subsurface structure of Europa.
Yeah, so can you talk about that just a little bit more? So Cassini carried a radar that could see the surface, but a sounding radar can actually measure and see what's going on beneath the surface. Can you talk about that a little bit more?
So it's designed to be able to, it sends out signals and is sensitive to, at wavelengths that will penetrate into the ice. And then it is sensitive to detect how those signals return and where they reflect in the crust will give us information. For example, if there is liquid water that's perched up closer to the surface than the ocean, that would be something one would hope to be able to detect.
These sounding radar technologies have been verified and tested with the Antarctic.
It's a longer wavelength.
Oh, okay. So this beam of something goes down, and does it move, or I guess does it travel at different speeds, whether it's solid ice or liquid? I mean, how do you tell the difference between the different structures?
Right. So the simplest thing to think about is that you'll send a signal and there'll be a reflection off the surface.
Okay.
Right, and so that's very easy to think about because it reflects off the surface and you receive it, which gives you a measurement of the altimetry, of the topography of the surface.
Yes.
But then you're exactly right.
Okay.
There will be waves that penetrate into the surface, and you can detect when they come back, which tells how far.
This is a fancy way of describing the same thing that happens in optical wavelengths when you look through stacked sets of glass, where each layer of the glass might have slightly different transparent things embedded in it. So if you look at a stack of stained glass, you can visually see the surface and each progressive layer because light is passing through and reflecting back from each layer. This is doing the same kind of thing with much longer wavelengths that penetrate ice.
Hundreds of meters into the methane seas on Titan. But what the radar on Clipper is designed to do is penetrate kilometers into the ice shell so that we can understand the structure of the ice shell.
That's
it's really cool.
So cool.
Yeah.
So if our idea that there are subsurface lakes just a couple kilometers down is true, then we'll be able to see them.
User Steve asks, could there be non-carbon based life with completely different requirements for existence?
Oh my God.
And this is always a great question because the only life we know is the life we know, which is ours. And so we think we understand what we're made of and what it takes for us to live. But but what other ideas are out there? Could there be? How do we know what we don't know?
The best person to ask this question to is Peter Ward, who's doing research on this at University of Washington.
I don't think I know enough to. Well,
for water-based life, the water is a solvent. That enables the materials to combine. And there are other solvents, and so it's quite possible to think that there might be life based on the other solvents as well.
Absolutely.
Yeah, I mean, in the lakes of Titan, methane and ethane and lots of other things, those aren't water, so if there's life there, then it would be...
Right, it's possible that there might be places where there are
So
sure.
So she's referring to
That's still
Titan.
carbon-based.
it's carbon-based, but it's not water-based.
But not water.
Not water-based.
Right.
Yeah, so it wouldn't require liquid water to exist.
Right.
Oh,
That's the difference. Sorry, yes.
Yeah.
It is
What else
carbon-based.
other than carbon could there be? I mean...
It's hard to imagine.
Yeah.
I
have no idea.
Silicon. There could be silicon.
Good question. We have another question from the media. This is from Bart Leahy is Spaceflight Insider. How close will Europa Clipper get to Europa, and how many passes will it make by the moon?
Cool.
The nominal mission design that we have right now has over 40. Right now we have 44 close flybys of Europa, and many of those get down below 100 kilometers, and several are down at the 25-kilometer altitude, just screaming over the surface. Yeah,
which is about
exciting.
15 miles. I looked it up.
Yeah.
That is mind-bogglingly close. I mean, that is.
Yeah.
What is 15 miles away from DC? You know, I mean, just like, right? Do we have? Can we give a reference here?
It's less than DC to Annapolis, I think.
Oh, for sure.
Yeah.
I mean, that's.
Yeah, I commuted
That's like-
further this morning into.
Yeah, like that's scary close.
Yes.
I mean.
So a better comparison is planes fly at about 35,000 feet, which is a little over 6 miles up. So we're looking at the Europa Clipper will get about twice as close to Europa as airplanes fly above the Earth.
Into them, the better sensing of the
closer
material.
you get to the source region, the better.
Exactly, and that's also better for measuring the magnetic field too.
Exactly, yes. Yeah, if you get too far away from the plume proper, let's say there is indeed plume, then the signals will be contaminated with other effects. You know, the plasma is interacting with Europa constantly. So if you're too far away from the plume region, you may not have a chance to really tell a lot about the plume.
And what different aspects of the plume can you find out from getting that close? And would you be able to see, you know, material falling back onto the planet, you know, or excuse me, the moon?
Right.
Well, one of the challenges of Europa compared to, say, Enceladus is that Europa is much bigger. So there's a lot more gravity. So when you see these images of Enceladus with the plumes stretching out almost as far above Enceladus as Enceladus is large, that's possible because there's so little gravity holding material back. But on Europa, material won't be able to get as high, especially some of the particulate material. So being able to fly lower through the plume gets you closer to the source, and therefore makes it possible, hopefully, to sample more of the material that's coming out.
It's in order to do what they want to do, they're just going to get closer to Europa than we ever got to Enceladus.
More about the magnetic field and the measurements that you took when you were at Europa. And Shunjan has talked a little bit about the magnetic signal that he saw in the plumes, but just kind of in general, what's the magnetic field like at Europa? And how many places in our solar system do we have a magnetic field?
Well, that's good. Let's start with how many places do we have magnetic fields? Not all of the planets have planetary magnetic fields. So Mars doesn't have a planetary magnetic field. Venus doesn't have a planetary magnetic field, but little Mercury does. So, and all of the giant planets. And as the Galileo made multiple orbits through the Jupiter system, we established how the field varies with space and time. And then we found each time we came close to one of the big moons, the field deviated from what had been present if the moon hadn't been there. And it's almost as if a boat is going through the water, and that pushes the water to the side and makes waves on the side. So as the material of Jupiter's environment encounters one of these moons, it gets diverted, it gets slowed, and the magnetic field changes magnitude and bends, and we can relate all of those changes to properties of the moons.
So basically, it's as though you were able to put an object next to a refrigerator magnet and change the magnetic field of the refrigerator magnet. In this case, it's Jupiter's magnetic field, and the different moons are changing how the field works.
The material that is coming out from Europa is probably electrically neutral. It's probably dominated by water vapor, which is a neutral material. But there are lots of energetic particles in the environment of Europa, and they ionize the material that is coming off. So they make it an electrically charged material, which can carry currents. And it's those electrically charged parts of the plume that cause the changes in the magnetic field that Shinja modeled so well, and change the density of the electrons in the environment that were measured by the plasma wave instrument. So it's not a direct effect on the environment from the plume. It's a two-step process.
Okay.
Wow. Thank you so much, Margaret.
Yeah,
That's
thank
great.
you.
Margaret is a retired professor. She served out her life finishing off the mission.
Really quite got this question from that angle yet.
Mm-hmm.
So what do we know about the bacteria, and could they actually survive at the temperatures that we think
Right.
Europa?
Well, the surface temperature is quite cold.
Right.
Just a little bit. Just a little
Well, how
chilly.
cold is
Now,
quite
yeah.
cold? How cold is quite cold?
I don't remember the solar.
I can. I mean,
Yeah,
I
I
can
don't
just
sure
look that
actually
up
at the
right
top of
here.
the
Let's
equator is
see.
about
Cold
100.
is,
It's about 100?
Yeah,
Thank
near
you.
the Kelvin.
100
about 100
Kelvin, which is minus 173 in Celsius, and you're gonna have to figure out what that is in Fahrenheit for me.
Right.
Let's see.
but that's pretty darn cold. But how
It
cold
is.
do we?
I'm really amused that the camera angle started to allow us to see the one computer screen, and so she tilted her computer. I suspect she's Googling the unit translation. That's just a guess, though.
Types of chemicals in the water, so it could be a little
Right.
colder than water,
But we know there are bacteria on Earth that can survive in very extreme temperatures.
Yeah.
And certainly liquid water in the interior of Europa would probably be quite toasty for some of those.
Okay,
For some of those
okay.
bacteria. Whether there are levels in the in the ice where things can survive.
right.
That's
a good question too.
exciting question
Right,
to study.
right.
Well, we do know of one extremely cold place that life
Yes.
can survive, right? Lake Vostok.
Lake Vostok, yeah.
Right, in Antarctica, correct?
Right,
Yeah.
beneath the ice shell.
Yeah,
Ice shell,
so
yeah.
do we,
Antarctica.
let's see, just, my quick internet searching here, it's about minus, 80, 90 degrees Celsius. So,
Okay.
we know there's some extremophile cold bacteria in there, or some
Okay.
maybe not bacteria, some microbes
Right.
down there. So I guess that's a start, right?
Good.
So, on Earth, everywhere we've ever looked for life, we've found life. So the question is that going to be true elsewhere with the same sorts of adaptations?
So that's a great question. So Shinja, you've looked at these plumes, at how high they are and a sense of how big they are. Is there a sense or a way for that material to
Yeah,
stay
that's a-
and perhaps be transported to another moon?
That's a
in
really
Jupiter's
excellent
system?
question. I think there Europa has also in the past been found to be a source of neutral particles, around the orbit of the moon. And it has always been a puzzling piece of information, observation we had, how to interpret the existence seemingly a neutral cloud around Europa. I mean, we have long been thinking of Io as the major source of plasma to the Jovian environment.
Because it's just spewing stuff
Spewing
out all
out
the time.
volcanoes, volcanic material into space. But Europa also seems to be important also in terms of providing neutral material. So we have to understand, the link between maybe whether or not plumes are responsible for those type of phenomena we saw in the past. But it's a
Okay.
great question. Yeah, I think it needs to be.
Good.
And we
good.
certainly see that in the Saturnian system. where
Sure.
Enceladus is the source of the
Sure.
E-ring. But yes,
Right.
also Io in the
And Io
Jovian
in the
Yeah.
system.
Jovian
So
system,
there's certainly a lot of exchange of material
Sure.
between.
Sure.
So this means that if there is life that is in the plumes, it could migrate between worlds, if it survives, which might be hard.
For Galileo, and then the mission flew, and it was flying around Jupiter and visiting Europa. Did you ever anticipate these types of discoveries would be made with the Galileo data?
It's amazing how hard it is to anticipate something that just hasn't happened before. Even discovering that Ganymede had a planetary magnetic field. One of the biggest moon of Jupiter had a magnetic field. That was really quite a surprise, discovering that we had signatures that seemed to require a sub-ice ocean at Europa. Again, it had been discussed as a possibility, so we were aware of the possibility, but it was certainly not of something that we thought was highly probable. And then when we saw that there really was a signature of an ocean, it was quite an aha moment. So no, I don't think I would have anticipated this, and certainly not anticipated that we'd be finding out about plumes 20 years after we acquired the data.
That's amazing. That's just incredible to be involved in those types of incredible discoveries. Thank you so much, Margaret. We've got, I think, a few more minutes left for some of our discussion, and then we've got a video to kind of close out our hour here. So maybe a few other topics. For one thing,
NASA press conferences are highly produced so that everything can get highlighted with all the message precisely communicated.
From these. So go ahead, Shinja.
So the one thing I feel extremely excited about was, having seen now this result from our paper really strengthens the case that, when you look also at the Hubble images, combining the two, kind of two independent piece of evidence, that now really strengthens the case that Europa seems to have plumes, and that really, I think, provides a great opportunity for future exploration of Europa.
Okay. All right, and I've got a quick media question they want us to squeeze in here
absolutely.
before we close out. So how important is it to send a probe back to Enceladus to get comparative data? And this is from Marcia Smith at Space Policy Online, and this is a great question.
So we're saying after Europa.
After Europa, yeah. I mean,
that's one of the exciting things in the outer solar system is the diversity of the types of objects we've seen. And we've today have only talked about the moons of Jupiter and Saturn. Only a few of the moons.
Only a few of those, right.
And the diversity of objects and the questions we have about moons as we get further out in the solar system, about Ariel at Uranus and Triton at Neptune. There's a lot of territory out there, a lot of terra incognita that would be really exciting to explore.
There is.
Translation, please give me an open checkbook and I will build all the missions to go to all the cool places.
Different places to each other, things that are similar and things that are different. We take, it's a lot of what we do. We look at how things work on Earth, and then we look at the other planets and make sure that we understand how things are working there. So this is a big part of our approach. So certainly getting to Enceladus would be fantastic.
Very powerful
to
technique
compare.
to do that comparison.
Awesome. That would be great. That would be great. So again, let's go back to Zibby here and see if you have some takeaway things that you'd really like people to take away from this discussion, from this new discovery, why it's so important to you, and going forward.
I think it really demonstrates how much we are leveraging future exploration and discoveries on past data sets, and how much richness there is if we go back to data sets with a new context, right? With the HST data suggesting there might be something there, going back and reanalyzing that shows us something we hadn't seen in the data before, and something we didn't know, and it and taking that in the context of Cassini, it just shows the steps we're taking moving forward. But it also just really whets our appetite for what we're going to be able to do at Europa. We're
so ready.
She's clearly very eager for the Europa Clipper to get launched and to get there. These poor scientists have to wait years to see their missions return data.
Sort of mine through. Right? Oh my God.
Yeah, so Shinja, what are you going to discover next?
We'll see. A lot of things to be learned, I think, in the old data set. Yes, definitely one thing I learned from this study.
A
lot of surprises.
A lot of surprises that The old data are still incredibly useful,
Yes.
right?
Yes.
The new data are great, but the old data are also, they hold a lot of
Yeah.
secrets we haven't yet uncovered.
Yeah.
So,
Yes.
so thank you so much for your work.
You're welcome.
Okay, I want to thank our audience, the listening audience.
So what he just highlighted is the importance of archiving data forever so that you can always go back and look to see what scientist wasn't recognized at the time because we just hadn't figured out the science.
The result is absolutely incredible to be able to say we really are confident there are plumes on Europa and have a mission that's really already in development,
Yeah.
going and ready to make those measurements is fantastic.
Yep.
So to close this out, we're going to leave it with another video with our Associate Administrator for Science at NASA. It'll be Thomas Serbuchen.
Today's announcement of yet more evidence of plumes jetting out of Europa marks an outstanding leap forward in our search for life and habitable environments in the solar system. There were hints of plumes in the past from the Hubble Space Telescope, but today's finding, which was mined from over decade-old data, gives us further evidence to sink our scientific teeth into. The fact that Galileo flew right through a plume tells us that on Europa, these plumes are common and calling us to explore. Europa has long been a high priority for exploration because it holds a salty liquid water ocean beneath its icy crust. In just a few years, the Europa Clipper spacecraft will be sailing towards that ocean world, equipped with the instruments necessary to investigate both the origins and the plumes and what ingredients they contain. Europa Clipper's ultimate aim is to determine whether Europa is habitable, possessing the ingredients we believe are necessary for life as we know it: liquid water, chemical ingredients, and an energy source. Europa's ocean is one of the most promising places that could potentially harbor life in the solar system. These newly confirmed plumes will provide another way to sample this vast ocean. Are we getting closer to answering, are we alone in the universe? The simple answer is yes. Perhaps that answer might come from a small ocean world like Europa. Thanks for watching.
And thank you, all of you, for joining me today. I still have other news to catch up on. Pardon me while I rearrange my screen for a moment. So that was a cool press conference in terms of summing up everything in a nice place where everyone was well prepped and able to just get out a clear message about what's going on. Now, if you would like to go read more about this mission and find out more about the science, for the Galileo mission itself, the Wikipedia page is actually pretty good. NASA has been working to get scientists updating all of the relevant wiki pages, and because this is an older mission, it seems to be sitting pretty fine. There's also a whole variety of different NASA pages which have more or less up-to-date information depending on which one you land on. Now, related to this particular press conference, there was a paper published today in the astronomy version of the journal Nature, and so you can go and read the scientists' results. It may be behind a paywall. Let me check that out. No, it doesn't appear to be behind a paywall, so I'm going to stick the direct link for that in the chat. Now, one of the things that amazes me with missions like this, and is part of why I like using already existing data pulled from the archive so much, is the older woman that we saw presenting on her Galileo work. She's a retired professor emeritus. This is a woman who dedicated many years of her career first to the almost decade and a half that went into planning and getting funded and getting launched the Galileo mission. And then it took years for the mission to get to Jupiter. And scientists have to be patient. It is, as several of you pointed out in the chat, the long game. So here we are playing the long game to try and find life somewhere else in our solar system. Now, beyond just talking about English, it's hard. Just talking about the Europa Clipper, there were other news stories out today. One of the most exciting, and I will switch images in just a moment, still recovering my desktop. One of the most exciting involves the idea of getting a happy little helicopter to Mars to test the ability of this kind of technology to work. So it's not so much that the helicopter is going in order to showcase the ability of helicopters to helicopter on the red planet and send back lots and lots of data. Rather, this is a mission kind of like the Pathfinder mission that occurred in the late 90s, where we're sending something tiny to test out, does this work? And once we prove the technology works, hopefully doing a little bit of science along the way, but without any big lofty goals, then we will work on sending more scientifically motivated vehicles in the future. And this little helicopter is going to travel attached to the belly of the Mars 2020 landing facility. There's a heat shield, there's the rover, there's everything that involves getting to the surface of Mars. It will be down in the lower parts of that. And then the rover will carry it to some place safe to deploy it, and then see just how well we can get a heavier than air vehicle to fly on a world with as thin an atmosphere as we see on Mars. Now, one of the caveats on this particular mission is the atmosphere on Mars is the equivalent of being 100,000 feet up here on Earth. And helicopters on Earth, they don't get that high. They get tens of thousands of feet up. And even then, they usually stay lower than 300,000 feet. This isn't to say there aren't special cases that can get higher. It's just to say they're not ideal at that altitude. So here we are trying to figure out how to create something that we may not even be able to really test outside of vacuum chambers. And here's to hoping that the combination of a lot less gravity allows it to figure out how to do all the things it needs to do. Like I said, here on Earth, helicopters go 40,000 feet up. This is the equivalent of 100,000 feet up. They're working to figure out how to build it as lightweight as possible while still powering it with solar cells. This is not something we do with Earth helicopters. And to carry around whatever payload it's going to need. Now, one interesting possible use case I already saw on Twitter earlier today is, well, as well as doing science, this little helicopter with its high-speed rotors also can potentially be used to blast off the solar panels on the 2020 rover itself. While Curiosity is powered with a radiothermal power generator, 2020 is not so lucky. 2020 will be another solar vehicle. Now, not all of today's news involves our own solar system. And in fact, our next story, and I'm trying to get the picture so that I can pull it up for you. Our next story is going to involve, well, what can we do with a gravitational detecting spacecraft that we use to look at globular clusters? Now, globular clusters are these truly amazing concentrations of stars that to be entirely honest, we don't completely understand their origins. They formed either slightly before our Milky Way galaxy or coincident with our Milky Way galaxy. And that basically means these are very, very old. They formed in some sort of a unique way such that they essentially had a single episode of star formation. So all of the stars in a globular cluster, they formed at the exact same time. This means that when we look at globular clusters, we can go, this globular cluster has this ratio of different elements in it. And based on those ratios, we can look to see what kinds of stars exist, look to see how old is the system, and then build all of that up to understand stars of this metallicity will age in this way. Globular clusters have stars of every possible mass, and side-by-side comparison of these different systems has allowed us to figure out things like, well, what is the variation in certain pulsating variable stars as you have them with slightly different masses? What is the variation in the ratios of different kinds of stars as we look at different kinds of systems? Now, one of the cool things about these particular systems is when we look at them, we see these amazingly dense cores, and this leads to lots of binary systems being able to form after the fact. These binary systems sometimes come into play when two stars pass too close together, gravitationally latch on together. Some of them may be original from when the stars formed. They formed in binary systems. All sorts of different ways exist in globular clusters to get these multi-star systems. And because these systems are exceedingly old, thank you, Master Coupon, for the bits. Thank you so much. Because these systems are old, the most massive stars have already completed their evolution and have left behind amazing stellar remnants. In this case, by amazing stellar remnants, I mean these systems have lots of neutron stars, white dwarfs, and black holes. It's hoped that in the future, when we launch the once again under construction LISA mission, which is a set of 3 different spacecraft that will be connected via lasers and be used to look for gravitational wave detections, once we have this system finally launched, it will be able to detect, because it works with different size gravitational waves than the detectors we have on the planet Earth. With its very different sensitivity, LISA will be able to detect black hole mergers in globular clusters, neutron-neutron star clusters, and all the other variations in between. So if we can just get LISA launched, and I really wish it had been launched when it was originally planned in the early 2000s, if we can just get LISA launched, we'll be able to study all the advanced physics of stellar death in globular clusters. And I, for one, am a fan of this form of stellar death. No one will be harmed. As near as we can tell currently, globular clusters are one of those places that you can look for planets and you're never going to find them. It's thought that because these systems formed so early and have so few heavy elements in them, that there just wasn't enough bigger atoms around, enough carbon, iron, all of these advanced atoms. There just wasn't enough around to form the planets that we're used to. Now, we could still be proven wrong in the future, but this is where we are for now. And this is the news I have for today. I will now answer any questions you have, and tomorrow there's going to be a special guest host, our newest scientist to join CosmoQuest, Dr. Andres Plazas. He is going to cover for me tomorrow while I'm in a different meeting, and you're going to start seeing him more and more around our CosmoQuest channel. So that has been a special edition of the Daily Space for May 14th. Tune in every day, Monday through Friday, to get all that's new in astronomy and space science right here on CosmoQuest X. We come out at 1 p.m. Eastern, which is 6 p.m. London, and 11 a.m. 10 a.m. out on the West Coast. Or 11 a.m. I'm not sure. This is why we have events that we are working to set up, or just give us a follow on Twitter and everything gets announced. Time zones are hard. Let us think it out and write things down for you. Anyways, thank you so much for hanging out today, and shoot me any questions you have in the chat. Thanks, and I'm going to switch views. So what questions do you all have? And I saw your comment about James Webb getting ever more delayed. One of the issues with the James Webb Space Telescope is it was asked to develop technologies that have never previously existed. And the scientists were given a budget that was about yay big. And scientists were not really good at budgeting. There's actually a research team out in Colorado that has been studying the differences between budgets produced by scientists as part of their proposals and budgets produced by people in the commercial world when they're writing proposals. And astronomers are really, really bad at budgeting. We're really bad. So with the James Webb Space Telescope, we had a bunch of scientists who are bad at budgeting by their nature, because it's not what we're trained to do, who are trying to budget how much it's going to cost to invent never previously existed technologies that will fly in space. Then we also have the issue that it sometimes takes longer to develop things than expected, and taking longer and requiring more budget just in general, both increase the costs, because you're now paying salaries longer and you need more supplies because it turns out you have to do this differently than what you thought. Put all of this together, you overrun your budgets, Congress puts you on hold, which also extends your budgets. Well, you figure out what's going on. The rocket you need doesn't actually exist. Well, now it does, because we are figuring out rockets again. JWST has just had a hard time. Yeah. They haven't had the unlimited budget that, as Dave Killens is pointing out, that the Manhattan Project had. So I see a question from Master Coupon. If globular clusters don't form many new stars, they don't form new stars at all. Are they mostly made of small, long-lived stars? Yes, that is exactly what's going on. Their main sequence has evolved away all of the biggest stars, and what's left behind are the itty-bitty little happy things that will live for millions and millions and millions and millions and sometimes trillions of years. And I don't actually mean millions, I mean billions and billions, but I'm not trying to quote people. So since we're down to the stars that last on the main sequence at least 15 billion years, we're looking at systems that have smaller stars, smaller than our own sun. And everything else is evolved. You may have red giants that are evolved stars, but you're also going to find neutron stars, pulsars, black holes, all the remnants of, well, what were nuclearly fusing prior stars. And I see someone whose name is really hard to make out on my screen. Let me try highlighting it to see if that helps. The Chladnin Nebula. Nebula? I'm not sure how to say your name. Welcome. Yes, we are going to have globular clusters that are made primarily of red dwarf stars in the future, in terms of things that are glowing brightly and not just dead stars in the process of cooling off. It's going to be a while before we get there. Those white dwarfs take a long time to cool off to red. chai latte. That I wasn't seeing that. That makes a lot of sense. A chai latte nebula, I can completely get behind. So Master Coupon is asking, do the clusters have a similar proportion of dark matter to normal galaxies, or can we tell? So we're in the process of trying to figure this out. I don't actually remember the results, but let me look it up. I know that dwarf galaxies, which are about the same size as globular clusters, are extraordinarily rich in dark matter. I just don't remember the globular cluster ratio. Sorry, I'm reading a paper real fast. So it looks like, according to a paper by Abata Napati, Solima, Belazai, Chapman, and D'Alessandra, that globular clusters are going to be less than 10% made of dark matter, which is a significantly lower percentage or proportion than we find in our own Milky Way, and way less than is found in dwarf galaxies of the same stellar population. So are there any other questions out there? Oh, what does it mean in the paper by plasma waves? Okay, so I assume that you're talking about the paper I posted a link to about Europa, Peter? See you, Larry. So if you're referring to that paper, I haven't finished reading it in its entirety. It only came out like an hour before I started this show. So the environment around Jupiter has this extraordinarily strong magnetic field. And there are ionized particles that have had a few of their electrons removed or additional electrons added on. I believe in this case it's removed. There are a bunch of ions being given off in different reasons in the Jovian system. And these ions end up forming plasma arcs in the magnetic fields. And you can end up with different waves. So this is where you think of the density changing throughout the plasma trapped in the magnetic field. You also get waves where you have the interactions between the moons, the magnetic field, and the plasma around the moons. This is an extraordinarily dynamic system that's really hard to explain because it involves all the things that astronomers struggle with. It involves dust, it involves magnetic fields, and it involves plasma physics, which isn't nearly as bad as the dust and the magnetic fields, but it's still hard to deal with. So I wouldn't quite say that it's electrification, Peter, because that seems to imply electrons flowing through a material. This is more like a bunch of charged particles, ions, moving along the magnetic field. It's okay, Guido. You are allowed to eat. Yes, today's episode was extra long because of the NASA press conference. So I'm not seeing any additional questions at this point. So thank you all for joining me today and for being a part of all of this. And yes, we're talking about not necessarily charged water, but charged molecules in general, charged atoms in general, Peter. I appreciate all of you sticking around for the entirety of the episode. Please come back tomorrow, same bat time, same bat channel, and we will be bringing you more news from CosmoQuest. Tomorrow we will have a guest host, Dr. Andreas Plazas, and I look forward to you all meeting him and asking him questions. And of course, there's one new question coming in now. Are there any missions coming up that could confirm if we found any Thorn Zeitkow objects? I don't know what those are, so I have no idea. No idea. I'm sorry. thank you all. Thanks you all for coming and being a part of the show. As I said, every Monday through Friday, we'll be here, and I hope to see you then. Wherever you are in the world, have a fabulous morning, evening, or afternoon, and keep up the science. Bye-bye.